covered already, and also about its impact from various speakers. And we're going to take you more back up into the air now to see where it all comes from, how it arrives at your ecosystems that you're going to study, and also talk a little bit about historical trends and what does it do when it gets there. You've already heard a lot in more detail from various speakers, and maybe how we can make it less bad. So, as you've already heard, nitrogen comes in many forms, and it gets emitted from various processes from the landscape. So we've got agriculture for ammonia especially, mainly from manures and fertilizers, and industry and transport. And it all goes up, it gets blown around by the wind, and you all have seen plumes coming out of chimneys. And then it carries on, there's various reactions in the atmosphere. Some bits of nitrogen react faster than others, we'll get to that in more detail. Then it dry deposits back to the surfaces and have an impact on sensitive vegetation, or it ends up being caught in rain by the clouds, gets caught in the clouds by the rain, and then comes down as what's called wet deposition, and also it can travel quite a long way as long-range transport around the world. And of course there's also nitrate leaching, so we're not talking about nitrate leaching today, and we're also not really going to talk about nitrous oxide, the greenhouse gas, but focusing more on ammonia and NOx emissions. So, as I've already said, ammonia comes mainly from agriculture. These are your sources. It's what comes out the back of the animal, the manure and the slurry, and that has lots of nitrogen in it, which then emits. And it emits during all the different stages of livestock management. So you've got your animal housing, where the manure gets dropped. You've then got manure storage in heaps or in tanks. Then you have the land spreading of the manure. This is a particularly dirty example of spreading manure. And also, of course, the animals grazing on the fields as well. But you also get ammonia from excretion from other animals, seabirds in particular with their fish-rich diets. And seabird colonies are a real source of, localized source of emissions that can be bigger than a large chicken farm. Seals, but also cigarettes contain ammonia. It's one of the ingredients that go in. Humans breathe out ammonia because they eat nitrogen-based food, and they excrete nitrogen, and babies' nappies, and also sweat contains ammonia. So sometimes that smell you get from sweating is ammonia. And there's all sorts of weird and wonderful studies that we've gone through and read, medical journals, and it's just a minefield of different ammonia sources out there. And also car exhausts contain ammonia. So that's your main sources of NOx, mainly combustion, industry and transport. Again, cars, aeroplanes, ships, buses, trains, and industry and power generation. So effects, very, very briefly, we've got our ecosystem effects on plant species and communities which change with additional nitrogen. Plants also get, because they grow so much faster, there's more water in the plants, so then they become much more vulnerable to droughts and frosts, and also because they're much nicer and juicier, pests and pathogens are more interested in them. Human health, if you breathe in lots of NOx, especially in polluted roads, your respiratory and circulation system can suffer, and if you've got asthma, it's even worse. It's also increasingly, and this is particulates in general, not just nitrogen as such, increasingly implicated in major health issues and NOx as well, ranging from low birth weight. There's a correlation between living in a polluted area and babies being smaller, and apparently even diabetes, various enzymes and things change, and you're much more susceptible to diabetes even if you're otherwise living healthily. And there's also research that suggests there might be links with Alzheimer's. So really, air pollution, NOx, and possibly other forms of nitrogen as part of particulates really are something to worry about. And if you're talking stakeholders, it's much more easy to get people to spend money on human health than on rescuing some lichens. And of course, this whole thing filters through all the ranges: water, air, greenhouse gases, ecosystems, soils. So while we're talking air here really, and effects on ecosystems, it just permeates through the system. Again, Mark Sutton started talking about historical nitrogen. We're not going quite as far back as he did on the Silk Road, but atmospheric nitrogen has become increasingly important over the last 200 years. Some of you may have heard at some point in your studies about the Great Smoke of London, when there was so much pollution in the air, and it was a mix of nitrogen and sulfur dioxide from all the burning of coal. I don't know how many people died, but it was several thousands, and it was really so foggy that they had to walk in front of the bus to guide it to find its route. That picture of the chimneys from Leeds, that's what it used to be like when a lot of coal burning was going on. Population growth. All these people need to be fed, and all these people have various practices that, I mean, ammonia, they go around by car. If population grows, more cars, unless you sort the whole system out. The seabird guano industry, before the Haber Bosch process was invented, people were mining these seabird islands and just shipping from the islands of Chile and Peru, shipping guano across to Europe for people here to fertilize their fields. Pig density, I'll just move on now. It used to be a completely different picture. In the early years, everybody had a pig. Every small farm unit had a few pigs. People in villages had pigs. And as you become more specialized and more industrialized, the pigs just start to become very much concentrated in particular areas where the more intensive farming is happening. So it's really changed quite a lot over the last hundreds of years. And emissions have gone up. So these are the agricultural emission sources through the last 200 years. You can see that cattle have massively increased in numbers, have started to come down a bit again. We're using mostly UK examples here. And the horses, the red, they have gradually disappeared over the more recent period because they're no longer used so much for farming and carrying people around. So if we're looking at emission trends, really the Industrial Revolution has a lot to answer for in terms of all these chimneys going up and all the pollution caused by burning a lot of coal. Domestic coal use for heating houses peaked around 1900. Then motor vehicles, which came in early in the 20th century, increasingly got popular. More and more cars appeared, and they did not have catalytic converters in those days either. The Haber Bosch process was commercialized in around about the 1950s, and from there onwards, the mineral fertilizer use just took off. Peak sulfur emissions in the 1970s, and with the forests dying, the acid rain problem, that was recognized fairly quickly, and everybody then got together and said, this is a big problem, so we must do something about it. NOx emissions peaked in the 1990s, and that's when the catalytic converters were put in. Ammonia emissions also peaked then. And policy interventions at the international level really made a big difference. And given how far these pollutants travel and that they don't recognize boundaries, political boundaries, it really had to be an international effort. So NOx has reduced in the UK by 90%, great policy success. Sorry, SO2. NOx has come down by about 50%. It's still in progress trying to clean up factories a bit more. They're now going for medium-sized plants rather than just the large ones. And ammonia emissions, unfortunately, there's very little reduction, and it's mostly stable, mainly because the farming community is a big lobby, as Mark said earlier, and it's not being tackled so much. And it's also not quite so easy, because there are all these thousands of farms as opposed to maybe a dozen big power stations. And if you have just 1 dozen power stations, you can really put the filters on and that's it done. You can't do that with every farm. Oops, too fast. So SO2 emissions have come down. This is from our national inventory. The NOx has also come down, and these horizontal lines here, that's the current emission ceilings. So the UK is doing all right, but with the ammonia, the targets aren't very ambitious. And we'll get back to that later. So we then modeled emissions and deposition for those last 200 years, looking into all these really wonderful data sources. And you can see the total nitrogen has come down, but the green line, but that's mostly due to the oxidized combustion sources reducing rather than the ammonia, which has just had a smaller dip, which was partially just due to animal numbers reducing for various economic reasons, a little bit of reduction in fertilizer use. And you can see here on the maps just how much nitrogen has changed over the last 200 years, from barely anything to industrial revolution industries. You can see there's London, there's the Midlands with Manchester and Birmingham and all these other industrial cities, increasing more with more population. Haber-Bosch just starting to kick in, then really the fertilizer coming in the rural areas, and then gradually starting to reduce again, mainly due to the NOx reductions. And there's further predicted reduction due to existing policies. However, that's mainly due to NOx policy, not to ammonia policy. Okay. At that stage, I shall hand over to Ed and have a little break.
Okay, so I'm going to talk about sources of ammonia, sources of nitrogen currently in the UK. So in terms of reduced nitrogen and ammonia, in the UK it's largely down to agricultural livestock. In the UK, this is all emissions coming from housing, storage, land spreading of manures, and grazing emissions, which is an important distinction you'll see in a minute. We've got 15% coming from fertilisers, and only 18% coming from other sources, including non-agricultural animals, anaerobic digestion, which is increasingly becoming more popular, and it's a way of turning waste products into energy, and small sources coming from wild animals, composting, sewage, other sources. So if we look at Portugal, it's a similar picture, and although it looks very different, it's because livestock for this data source, which is the EMEP emissions, for livestock is just housing manure storage. So the grazing and manure application is included in this pie, along with fertiliser emissions. So the actual picture is pretty similar between the two, despite it looking slightly different. And other sources coming from industry, waste, road transport. If we look at NOx, in the UK, 32% is coming from road transport, 23% from power generation, 45% from industry, which is sort of metal production, other industrial combustion, and only a really small percentage, 0.004%, coming from other sources. Similar sources in Portugal, slightly larger proportion of road transport, 32 to 43 percent, which might be older cars that haven't quite got the same technology in terms of catalytic converters and things. Smaller proportion for power generation at 11%, but on the whole, similar sources and pretty similar in terms of emission sources. So if we look at the spatial distribution in the UK, these emissions, For reduced nitrogen, which is ammonia and ammonium, the spatial distribution, for those who don't know the UK very well, is typically the rural areas, so where the livestock is and where fertiliser application is, and sort of more agricultural regions. Whereas for NOx, this is population here. The NOx emissions largely follow the same spatial distribution as population, because these are things like road transport, power generation, and distributed in the same areas as the cities and the built-up areas. And I think at this point I'll look back over through.
So a brief interlude on atmospheric processes. Not to worry, we're not going to look at lots of equations. Alright, again. So just to remind you, emissions go up, there's chemical reactions, and then they come down again by various means. And ammonia is very highly reactive, and it's not acid, it's a base. So it then reacts with all the acids that are in the air, such as sulfur dioxide or NOx and various other things. And because it's so highly reactive, it also dry deposits very quickly. And there are very steep gradients then in concentration from a source to where it comes down again. And also the dry deposition happens quickly. So here we have an old example from measurements in 95, 96 done near Edinburgh. There's a chicken house here, and measurements upwind and downwind, and you can really see the gradient drops off very, very quickly from very high concentrations right next to the chicken house to nearly back-to-back ground within 200 meters. No, wrong direction. Ammonia is quite complicated. You might have already gathered that from various people. So it has what's called, it does bidirectional exchange, which means depending on the relative concentration of ammonia within the plant and the air above it, you get emission or deposition. So if you have highly fertilized crops and the air above them has less concentration of ammonia, you get emission from the plants. If you have a lovely bog with very poor nitrogen conditions and you get a plume of ammonia coming across from a chicken farm, it will go straight down into the plants and be deposition. So dry deposition depends very much on turbulence. So if you have a woodland, you have a lot more rough surfaces there, and therefore the ammonia will come down faster on a woodland than on a smooth, well-cropped grass surface somewhere. So that's turbulence and surface characteristics, because obviously obstacles such as a woodland creates turbulence, and then it's these relative concentrations which cause the bidirectional exchange. So ammonia might just go up and down several times depending on your conditions locally. And with wet deposition, it's higher in high precipitation areas, obviously. Quite complicated in other ways as well. So depending on the temperature, you get a different percentage of the nitrogen volatilizing as ammonia. So if you put down a slurry puddle in a cold place, the ammonia just sits there, but with roughly every 5 degrees Celsius in temperature increase, you double the ammonia emissions. So, in order to test that, Mark's already mentioned our lovely project measuring ammonia from seabirds across the globe. So we had hot places such as Ascension Island or Michaelmas Key on the Great Barrier Reef. We had the Isle of May in Scotland, which is temperate cool, and down here on Bird Island and Sydney Island, we have penguins. So we can see here the average temperature during the measurements and the percentage of ammonia volatilized. So on the penguin colonies, very small percentage, less than 10%, less than 5% of that nitrogen that is in the very rich seabed guano goes up into the air as ammonia. A puffin colony, now you might have seen pictures of puffins, these lovely small birds that look like parrots, and they burrow in holes in the cliffs in Scotland and other northern European places mainly. Because they bury in holes in the ground, the ammonia actually gets recaptured within the cave where the chick lives and grows up. So there's a smaller emission here. But then if you go to the vast rock, which is a big rock just next to Edinburgh, and it's bare rock, so the birds just maybe put a few twigs there, but it's basically bare rock, so it doesn't infiltrate, it just sits down and then emits. You get higher emissions here. In a warm breeding season, warm by Scottish condition of 17 degrees. And then as you go to Ascension Island, it's 30 degrees, but the reason that volatilization is much lower there is because it's so dry that you can't really get much emission of that. But as soon as you get rain, and we had a couple of rain pulses, it just shoots up all at once. And then Mid-Life E, which has a picture here, they get basically a bit of rain every day. So that was a nice example of using similar management practice, if you like, as in the birds just put their droppings there and then things happen based on the environmental conditions. Whereas if you were trying to do the same thing with agriculture, it's very different depending on what methods you use to apply your fertilizer, what your soil conditions are and so on. And it's much easier to work with wild birds. So thinking landscape and how quickly ammonia deposits. So we were measuring with alpha samplers, which Pedro was already introducing earlier for the southern Portugal study. You can see this is just 2 kilometers here, so that's a 6-kilometer area. And there are lots of chicken houses in here. We get high concentrations near the chicken houses, but as soon as you go a couple of kilometers away, it's gone. This is more of that same landscape. So here we've got a bog. Here is Wim moss, which you have seen some examples from, but you'll see more in a little while. Here are all the chicken houses. Because luckily the wind is coming from the southwest, it doesn't go straight onto Wim bog here. So there's a chicken farm right here. And if the wind was going easterly, it would blow straight over that protected site. Luckily it's all going northeast most of the time. So this is what the landscape looks like. It's sheep grazing, cattle grazing, and all these chicken houses. There'll be more examples of that later. Then zooming back out a little bit, landscapes are quite variable. And so you've got your chicken bit, you've got your grazing bit, you've got your bog. And if you zoom out further in the UK, we've reclassified our emission maps to look at what we call dominant sources. So all these hilly areas, the green areas, is where cattle make up the majority of the ammonia emissions. Up here in the Scottish Highlands and Islands, there's so little emission, it's less than 1 kilogram per hectare for most of the area. That's what we call background. And over here you can see the orange, that's where it's mainly crops and hardly any animals. And the red has got lots of pigs and poultry, which is specialized in this area here, and it overlaps with the crop area, but it's so much stronger that it dominates the local emissions. And here you've got your urban centres, such as London. Oops, fast. And then if you zoom out a bit further to the whole world, what's the global sources here? So again, we have got the northern latitudes and the deserts and the Amazon rainforest where there isn't much of an emission happening because human activities are missing there. And we've got seabirds down here dotted around quite a lot as the main and only source. That's agriculture dominating quite a lot. And in the tropics there's also a fair bit of biomass and waste burning. And at that stage, I think I'm handing over to Kate.
Okay, so I'm going to be talking about the bottom-up inventory approach, which I think Mark Sutton and Jose briefly touched on yesterday. So looking at how we take information on activities and produce emission maps and services based on that. So as we said already, in terms of agricultural ammonia emissions, Animal emissions come from housing, storage of waste to be spread on land, slurry tanks, things like that. As Mark was saying yesterday, manure spreading, particularly in the UK, old technology of splash plate spreading. And I should probably say at this point, when we produce emission factors, we're using average practice. So whilst in the UK most of it is done by splash plate spreading, we also take into account that some farmers will be adopting more modern technology and injecting manures, and also using trailing shoes and other technologies. And we've also got grazing emissions. So in terms of different livestock types, the proportion of these emission sources is quite different. So for dairy cows and heifers, the majority of emissions come from housing, because they're largely kept inside. Some storage of manures, spreading of these manures, and only a small proportion coming from grazing emissions when they're outside. Whereas for upland sheep, that typically in the UK left outside all year round, in the upland regions, the vast majority is coming from grazing emissions, with only a small fraction for housing, industrial lambing, and storage of manures when they're used. And again, for laying hens that are largely kept inside, majority of emissions coming from housing, small portion from poultry manures, storage, and land spreading and grazing. So this map here looks at how we take activity data. So this is at county level, I think, for the UK. So we get sheep estimates at the county level, and we distribute these county totals based on land use, relating to where we think these emissions are likely to come from. So in a county, we're estimating that 79% of the sheep are likely to be on improved pasture, 20% are likely to be on semi-improved pasture, and 1% on the sort of quite marginal unimproved pasture. And then we produce these estimates of sheep per hectare that we can then apply emission factors to and produce emission estimates. And then we produce these layers, so agricultural emissions for each of the agricultural sectors. So we've got cattle, and like Uli's dominant source map showed, sort of Devon and Cornwall and this west coast is largely cattle dominated. Poultry tends to be East Anglia in the east, and a few quite intensive towards the northwest. And these emissions are quite often in sort of suburban areas due to sort of intensive pig and poultry farms, and similar distribution with pigs. The east of England and Scotland is dominated by fertiliser in production of crops. Sheep, typically in the upland regions, in the UK, Wales is famous for sort of sheep and lamb production. So this is reflected here in the distribution. And because they're all the same scale, agricultural horses currently typically make up very little emissions, so are all under 10 kilograms of N per hectare per year. And then adding all these agricultural sources together, we produce a map of total agricultural emissions that we can then report to the inventory, and we can then calculate deposition based on these estimates. So if we look at total reduced end emissions, as I showed before, typically dominated by agriculture, so it's largely got the same spatial distribution as the agricultural emissions. And the emissions that get turned into dry deposition largely have the same spatial distribution as the emissions. This is because, like Uli showed, the ammonia gradient is very quick to deposit, whereas the wet deposition largely gets deposited in the upland areas where we receive high rainfall in the UK. So this is sort of Snowdonia in the uplands, the Pennines here, and where in the UK we receive lots of rain. And adding these two together, we get a map of total deposition. And similar for NOx. So as we said earlier, some NOx comes from shipping lanes. That's why I've got this kind of crazy distribution around the UK. From the major cities and urban areas. And similarly, although it's not as quick to deposit generally, we get a similar distribution in dry deposition to the emissions and the wet deposition in these upland regions again. To produce total deposition. So we're now going to look at the spatial variability and how different estimates at different scales sort of impact the estimates of N, and why it's important to always use the sort of finest resolution data you can to produce the best estimates of N emissions and deposition and concentrations. So this is an illustration of the EMAP model that's a free to download atmospheric transport model. So it takes emission data and translates it into deposition and concentrations. One of our colleagues, Massimo Vieno, set up the EMAP model for the UK, and he's used this nested sampling structure. So he uses for the far actually I'll go from the centre. So for the UK, he uses 5 kilometre grid resolution emission data, which is what we're producing here and here. So you use that information in the model. For the countries surrounding Europe, sort of more intermediate area, he uses 10 kilometre grid estimates. And then for the rest of Europe, because it affects the UK less, he uses a lot coarser estimates, just these sort of computational reasons and also availability of data. So if we look at critical load exceedance, and Mark Sutton shows an older version of this slide yesterday, at the sort of 50 kilometre resolution, you get broad trends and you can see where nitrogen critical loads are being exceeded throughout Europe. But if we look at this area of Devon and Cornwall in the UK, by switching to a combination of 1 and 5 kilometre data, so this is 5 kilometre deposition data and 1 kilometre estimates of critical loads, we can see exceedance here, and you can get a much better idea of where in the landscape critical loads are being exceeded and where nitrogen mitigation should take place. And then a PhD student worked at CH Esther, looked at critical load exceedance at the landscape scale, and you can really pick out where surrounding sort of large agricultural sources, areas should be targeted, and much better than these sort of coarser data. And so this is looking at agriculture, so this is the map I showed earlier, with all the agriculture sectors added together at 5 kilometre resolution, and you can really pick out the sort of areas where there's intensive cattle, intensive fertiliser, the upland regions, much better than this 50 kilometre EMEP data that you can download readily, where although it's got the same general trend, when you look at a certain region, it's much more general estimation. If we look at ammonia concentrations versus ammonium, so ammonia, as we said before, deposits much more readily than, or deposits readily from emissions to deposition. And you can see that this produces quite a sort of heterogeneous surface compared to ammonium that's more related to wet deposition, where you get sort of general trends. And so for ammonia, it's important we capture this variability much more than ammonium, where a sort of 50 kilometre grid resolution estimate could actually produce quite a sort of decent representation of what's happening. So if we look at the spatial resolution of ammonia concentrations, this is the 50 kilometre EMEP representation for, do you know where this is? I can't make out
I
really.
think that's somewhere in Scotland, isn't it?
Yeah, somewhere. So for the 50 kilometre, we're getting an estimate of 4.5 micrograms per metre cubed. When we move to the 5 kilometre grid resolution, we're getting a slightly higher estimate, and you can see areas that are only 2.5 micrograms, and this sort of area where it's a lot higher concentrations. And then moving to 1 kilometre, you can really make out the sort of distribution where there's less concentrations compared to down here, where the concentrations are above 6 micrograms per metre cubed. And if we look at this on the landscape, so here we've got Ingleborough Complex, which is a Natura 2000 site in England. And this sort of intensive upland agricultural landscape with a few intensive pig and poultry farms nearby, so sort of about 5 kilometres from the site boundary. And on the sort of north-east of the site is an upland area where there's little agricultural activity. So if we overlay 1 kilometre ammonia emissions on top of this, so this is a 5 kilometre grid, you can see that having this fine resolution 1 kilometre ammonia concentrations really picks out the sources, and you can see that we get elevated concentrations surrounding the intensive pig and poultry sites, and the ammonia concentration reduces as we move away from the sources and into the upland environment. And the 1 kilometre data really differentiates these agricultural regions to this upland region where little activity is taking place. Now if we look at, so generally emission inventories happen at an annual period and annual estimates of nitrogen. However, we know that different times of the year we can see elevated concentrations and emissions, and also different times of the day, sort of rush hour and things like that, we see increased emissions and therefore concentrations. So now we're looking at how we can capture this temporal variability. So this is work done by ex-PhD student at CH, Sophie, looking at how ammonia concentrations differ throughout the year. So this is information that's come from the ammonia monitoring network in the UK, and they're being characterised by what sources surround the monitoring network. So a site that's typically characterised by cattle, you can see that we get slightly elevated periods around the fertiliser application periods, and for the sites surrounding sheep emissions, you can see that we get more emissions during the warmer periods, and also following lambing periods. And use this to produce a monthly emission estimates, monthly agricultural emission estimates of ammonia. And you can see that during these fertiliser application periods, we get elevated nitrogen emissions. And then, hopefully this will work. Massimo runs as this. So he runs these concentration estimates based on forecast meteorology, and you can really see the sort of diurnal variation in nitrogen is sort of take place throughout the day, so rush hour and things like that, and also periods of high temperatures, and we can use this information to produce hourly estimates.
The resolution?
I think, do you know really? I think it might be 0.1 degrees, so roughly 10k.
Depending on where you are in the world.
Yeah. But yeah, it's a massive model to run, just because so much data involved in meteorology and everything.
And you can see the NOx and ozone interactions. They're quite nice.
Yeah.
How do you see the ozone interaction with the
So if you
blue shadow?
right now you don't see the interactions, you need to look at both of them at the same time to see how the ozone and the NOx react with each other.
Yeah, so the ozone is a blue one.
The ozone was on the left
On the left,
and the NOx
on the right.
on the right. I'm not stopping.
Oh, I see.
I might be able to just go back, because I don't think we need to.
So
Yeah, perfect. Oh, no, on 3.
So we've talked you through the bottom-up approach on the modelling now, and of course, models, if you don't constrain them, they can just go all over the place, and you need to be very careful with models. So that's why we need monitoring networks. And in the UK, we're very lucky that the government invested in monitoring networks, and we've got a good range of NOx, mainly rural actually, and urban. We monitor wet deposition, so we catch rain and then analyze it for nitrogen, which is fortnightly and in most places, and daily in 2 places, and the ammonia concentration network, which is monthly samples. And we need all of those to compare against the model's estimates to see where the model might be going crazy, and then try and Massimo's model where he compares here just for Birmingham the concentrations that he models versus measurement on the street. So this is obviously not monthly, but much better data from the AURM network. And you can see it fits fairly well. There's the odd peaks where you get something different from the model and the measurement, and that's where you then need to interpret whether, say, modeling is doing something crazy, or whether your emission sources are wrong that go into the model, or whether your monitoring site has just not recorded anything for these days. But in general, you can actually track down what's going on with enough information. And in this particular instance, it fits really well. The other model that we use is the frame model, which we're setting up with Pedro and team for Portugal, and we've got first results. So the key thing for ammonia concentrations is that the measured concentration and the model concentration ideally should match along the one-to-one line, but that never happens. And one of the reasons it doesn't happen is because, as I've already said, these monitoring sites in a landscape, it really depends on where they are, what they pick up in the surroundings. So if you have a site right next to a chicken shed, that will massively overestimate your concentration compared with what's happening on average in that 5 kilometers square. If you have your monitoring site right in the middle of a nature reserve, away from all the sources, that will massively underestimate what's happening in your whole grid square. So there is that. And there is also, obviously the model won't get the chemistry exactly right. The emission map might not be exactly right because a lot of the emission sources we have to distribute using various proxies. And agricultural practice differs. So for example, there might be some really dirty farms in one part of the country and not in the other. So that there's all these variabilities that we need to take into account. And fitting within that wedge is actually pretty good for a model. So, fast. Sorry, giving you a preview there. So, going back to the landscape scale, in this study landscape that I've already shown you a few slides of. So here's Wimborg, and here are all these chicken farms. And if we use the best emission factors to try and calculate emissions that match the local agricultural practice. So using exactly the type of chicken shed factors for some very high-tech sheds over here, which are where the birds are indoors, versus free-range sheds where they are open and the birds can walk in and out, and there's a lot of free airflow from the manure that sits in the chicken house to the outside world. So here we've got about 500,000 chickens in this shed, and here we've got about 30,000 chickens dotted around on the ridge of these little plumes. So while high welfare chicken production is really good for the chickens, the ammonia manages to get out, and these chicken houses where the chickens are indoors all the time and have limited space, they're much better for the environment, but not so good for the chickens. So there's a dilemma, and there's all sorts of technological improvements on how they can make these sheds more welfare friendly, give the chickens more space, but then in the way the manure gets looked after, they can improve that side of it. So anyway, going back to the calibration, so you can see here the dots are where we measured for a whole year monthly data. The student went out and did a lot of walking and driving to collect all these samples. You can see in some places it matches really quite well, in other places it doesn't match so well, despite our best efforts at modeling. So we then took the measurements to calibrate the model and bring the concentration down. Because especially at close range also a lot of models have difficulty and they overestimate their position. And again, this is where the bidirectional exchange comes in, because these models don't do the bidirectional exchange. So there's all sorts of complications that I really don't want to confuse you with just now. Moving on to effects very briefly. So I've already mentioned health effects. And I don't really want to go into that anymore. You've already seen these pictures on ammonia and lichen biodiversity on these tree trunks in Northern Ireland. The happy tree maybe about 20 kilometres away from a not so happy tree. Again, we can try and model these special areas of conservation. We take our emission maps, create concentrations, then overlay those with where the special areas of conservation on Natura 2000 sites are, and then we check what is the maximum modeled concentration at each of those sites. So you can see here in the Highlands of Scotland it's quite clean, less than 1 microgram per cubic meter maximum concentration according to a 1 kilometre model. Down in some other areas it's still pretty clean and still below the critical level for higher plants, but above the critical level for the lichens and mosses. So again, it depends on where exactly those lichens are in the trees with the lichens, for example, in relation to those local sources. And then anything above the yellow is above the critical level for the higher plants as well, maximum. So that doesn't mean this whole Pennines Nature Reserve is exceeding the critical level. It just means somewhere in that nature reserve there is a bit at risk. And if we don't know where our sensitive plants are within a reserve, then we have to take a precautionary approach and say that bit that is exceeding might be the bit where those plants might be just about hanging on. So it's all about interpreting the data carefully. Again, you've seen these pictures already of recovering away from the source and still effectively close to the former source. What will we see if we go back there in another 5 to 10 years' time? We're all really excited about that. So fingers crossed, watch this space. We've already touched on reducing impacts from atmospheric nitrogen. What can we do? So the NOx, it's technology rather than anything else because it's mostly from combustion. For ammonia, we need to think very carefully. So most of these emissions come from livestock excretion and fertilizer application. If you think about this happening in the stable, if you then have a really good housing system that emits very little, then all that nitrogen gets retained in your manure and then sits in the slurry storage. If you then aren't careful, there's more nitrogen there to be emitted at the storage stage. If you are really careful and have a slurry tank and you put a lid on it, and then you have even more lovely nitrogen in your manure, which makes a valuable fertilizer, and then if you fling it all over the place, it'll just come out at that stage. So you really need to look at this whole flow of nitrogen through your system and make sure you are careful with it at every stage. And at the grazing stage, there isn't really so much intervention, and there's a lot more opportunity for the urine to filter straight into the soil and then do the fertilizing rather than sitting on a surface like in a concrete surface in a house where it can emit much more. So you really need to keep that in mind when designing your mitigation strategy. Can you read this? Is it too small? So this isn't really for reading line by line, but it shows you that there are different categories of measures. So you can introduce a slightly better matched diet. So if you match your protein intake to what the animals actually need, a bit like the vegetarian diet, if you don't overfeed protein beyond what the animal needs, you can save between 10 and 30% of emissions. It's really quite simple. And it might, so you just need to make sure you do that carefully, and especially for pigs and poultry, which are getting fed a formulated diet, that is actually fairly easy, and then it's the cost margins that stop farmers from doing it potentially. You can modify your housing practices, which could save you up to 80%, especially enclosed poultry houses. You can do a lot with it. You can just filter them, and pig houses. Manure storage, again, you can save between 50 and 90% if you cover it all up carefully, and modify application again. If you don't just fling your manure about, you can save up to 90% by carefully injecting it and doing that job properly. Fertilizer application practices, again, you can do that carefully, and you don't over-fertilize, and you use less volatile fertilizers. So for example, urea emits, say, 10% in the UK of the nitrogen you apply as urea gets emitted as ammonia. Ammonium nitrate fertilizer, you only get about 2% of losses to the atmosphere. So if you're a farmer and your price difference between urea and ammonium nitrate is less than what you would otherwise lose to the air, you might want to just think again. So if it's just a marginal price difference and the urea is only marginally cheaper, you actually retain more nitrogen in your soil rather than sending it straight to the atmosphere. Combustion measures for NOx. If you put on filters and scrubbers, you can save up to 70%. And road transport, again, it's fairly good savings to be had. Consumer behaviour measures, Mark touched on that quite a lot, for dietary choice, but you can also make transport choices. So if you don't insist on driving your own car just for yourself, as opposed to with passengers, or you use public transport, or you use your bicycle, or you walk, you can save an awful lot of NOx emissions. And the same with energy use. If you switch off that projector in between sessions, you can save a little bit, and the little bits can add up. There's also what we call spatial measures. So we're not actually reducing emission as such, but we are moving our sources around a little bit in order, or we don't put sources next to sensitive vegetation to then not reduce emission but reduce deposition to the sensitive areas. And agroforestry also has a role to play, and I'm going to get to that next. So landscape scale spatial planning measures designed to decrease the impact of emissions rather than actually reduce the emissions themselves. So in this example here, these shaded areas are nature reserves, and the dark squares are farmsteads. So if you put, say, trees around sources, then the ammonia can't escape. It gets, well, some of the ammonia gets captured in a tree belt, for example. Or you could equally put buffer zones where you only put low emission or no emission agriculture, or tree belts, again, to give them a little bit of extra space away from sources. That's a quick work through example of what would happen if you, in a model, put tree belts around farmsteads. So you increase deposition around, you decrease deposition most around the farm, but you also decrease it into the nature reserve. So the darker the blue, the more you produce deposition. And this is the reverse situation. If you put the tree belt around your nature reserve, then the ammonia still travels freely all the way up to that tree belt, but then, especially at the edge, you reduce your deposition a bit. Obviously, you can't do that everywhere, because if you have, say, a bog or another water-based system, if you plant trees around it, the trees will just dry out the bog, so that's not very sensible. A little bit more on the landscape scale. So back to our, what used to be NATO Europe project landscape study. So there were 6 landscapes dotted around Europe, and we were all looking at slightly different issues. So ours, again, was upland grazing of cattle and sheep, and this cluster of poultry farms in here. So you can really, at the local scale, see your sources in the landscape. And the concentration modeling shows you that this area here exceeds the critical level for sensitive plants around the area where the poultry sheds are, and downwind of the prevailing wind direction. If you then make a deposition map of that, which takes account of the deposition velocity, which takes account of your turbulence and other issues. So for example, on a woodland edge, because of the turbulence there, you get more right position. So you can see that here, you've got the poultry sheds, and this woodland here, it gets much more right at the edge, and then as the ammonia gets captured and filtered out by the trees, the far end of the trees is a lot cleaner. And then if you translate that deposition into critical loads exceedance, taking account of the sensitivity of each of the habitats, you can then see that these particular woodlands here are getting the worst deal, and this bog up here is not actually getting such a bad problem because of the wind direction in this particular case. So we can then also play with scenarios. This is the baseline. We're just zooming in here now to the chicken farms and our two little nature reserves of Auchencourt Moss and Wim Moss. Chicken farms right here and a few small cattle farms here as well. So you can see under normal average conditions, they're fairly okay. Even the lichens in there are just about hanging on. And then ignore this mitigate 4. This means the most stringent mitigation scenario we applied. It reduces a little bit, and the cleaner area gets bigger. And then we also played around a bit further, and we put in an extra chicken farm down here, which is just one of those small animal-friendly free-range sheds, and hey presto, it encroaches, the ammonia encroaches into the nature reserve here at a much higher rate. So you can do quite a lot of model studies, and you can actually get your eye when you walk through the landscape to make you spot where the threatened areas are. Handing back to Ed.
Okay, so now I'm going to be talking about how we use this model data to work out mitigation strategies and work out what sources are actually contributing to deposition at a particular area. So whether it's sensitive habitats or whatever. So we produce emission estimates from different sources such as road transport, from particular power stations, livestock sources, and all this, so all these different layers. So we can do what's called a source attribution run, where we use all this detailed information and detailed estimates of different sources, and we add all the sources by a particular source. So Drax Power Station, which is a huge power generation plant in the UK, and run these emissions through the atmospheric transport model and calculate deposition. And we calculate the deposition from the estimates minus this particular source to calculate this source's contribution to deposition. So here we've got Drax Power Station. We've also done the same for road transport. So this is the road transport network of the UK, where blue's motorways and green's the primary roads. And you can see the deposition from these sources largely corresponds with the sources of the emission sources. And then we've got the deposition from livestock, and it's similar spatial pattern to the emission sources we saw earlier. And just to say that all the maps are really using the same classification. So deposition from livestock represents a much higher proportion than roads, and in turn from Drax Power Station. And then we've also got deposition from fertiliser. And we've got 42 of these individual layers that we can then take a particular point. So at this particular point, we know that deposition at this source is made up of 24% livestock emissions, 19% comes from the European emissions, so that slide we showed earlier where we look at emission sources from the rest of Europe. At this particular point, 19% of the deposition at this site is coming from emissions from Europe and the Republic of Ireland, not shown here. 30% comes from road transport, and so on. I mean, you can use this information to then look at sensitive areas and see how we could minimise emissions and then in turn minimise deposition. So we did a project recently for Northern Ireland for one of the government agencies, and we looked at all the Natura 2000 special areas of conservation. And we characterised the sites based on the deposition they're receiving using this source attribution approach. So from this study, we found that agriculture contributes about 60% of total deposition to received by the SACs, and transboundary sources, so European sources and Republic of Ireland sources, contributed a greater proportion around the border, and especially this sort of southwest of Northern Ireland. And yeah, so in terms of the UK, Northern Ireland is dominantly characterised by high agricultural emissions, but less, because it's less populated, less is coming from road transport and other sources compared to the rest of the UK. So we also did a similar study for an English environment agency, and around surrounding London and the other major cities, road transport and more industrial sources made a much represented a much bigger proportion of deposition sites. And this is reflected in this slide where we look at, in terms of deposition, what proportion is coming from reduced nitrogen sources and what proportion is coming from oxidised emission sources. So reduced nitrogen coming from sort of agricultural sources, and the red coming from typically combustion sources. As you can see, for Northern Ireland, nitrogen deposition is predominantly composed of reduced nitrogen, and compared to the UK, non-agricultural sources are a minor contributor to N deposition. And then we've further taken this source attribution approach and looked at what proportion what proportion of deposition comes from locally depositing sources, so ammonia and nitrogen dioxide, and what proportion is coming from N sources depositing regionally. And for the sources depositing locally, for most, so this is a particular site, this is Ballinholme Bog, SAC in Northern Ireland. We can see that the species depositing locally largely come from emission sources that are agricultural, compared to the N species depositing regionally, so ammonium and nitric acid, which is smaller proportions going from agriculture, and more is coming from European sources, road transport, and sources from further afield. And this was characteristic of most of the sites, with agriculture dominating the locally depositing species, which means that we can then look to mitigation and look at how we can reduce these emissions in the nearby area, or as we were saying, plant tree belts, or implement more efficient nitrogen mitigation, so using trailing shoe technology or injecting manures rather than using splash plate or whatever. And then John talk through this one, I think. Yeah.
So this is a small nature reserve on the border between England and Scotland, and it's bog again, and these concentric yellow lines are 500-meter areas. So you can see in that landscape, we just took a Google aerial view and looked at what's surrounding the area, because 2 kilometers is that zone where we think a lot of the dry deposition is actually originating from. And so we can see there were some sheep here, there was a slurry lagoon here, there's a livestock house, there's a slurry tank, and actually on Google Street View, if you have that available for your country, you can actually look. You can drive down the street on a computer and see the slurry tank and see whether it's got a lid on. So it may not be entirely up to date, but it does make you look at the landscape with nitrogen eyes. So when you're going on your field trip, hopefully just looking at your oak trees and your grassland and everything, if you look around a bit more widely, you see there's a farm, there's some animals grazing, there's a slurry tank, there's a chimney in the distance which ways the wind blowing. So just try and bear that in mind, and hopefully all this invisible air pollution that you can only then analyze by looking at your plants or analyzing bits of plants or analyzing the air, you can actually get a pretty good idea just from looking around you. So that's everything I've got to say. Any questions?
Do you have questions for Louis?
Nope. Okay.
So you talked a lot about the road emissions and position around them. How significant do you think ship emissions from, for example, the North Sea, which has a lot of traffic? How do you think their emissions are significant to the position in coastal cities? Like, how significant are they?
When we looked at, so for the equivalent project we looked at for England, when we looked at sites, so there's the North York Moors site, which is towards the North Sea, and if I remember correctly, I think shipping was higher, and it was about sort of 8%. So this was using different source attribution data set. But for Northern Ireland, where it is a minor source, but at some particular sites, so North York Moors is further away from agricultural sources and is dominant, so it receives quite a lot of high rainfall. So sources from further afield were a high contributor to deposition at that site, and because of that, emissions from shipping were a bigger proportion than other sites. But I think it's not a massive source, but because deposition came from sources further afield, emissions from shipping didn't dominate that site, but were substantial.
And just to add to that, so ships used to burn really dirty coal compared to the coal that was allowed to be burned on land. So there are now international regulations that are covering the sulfur. So the sulfur emissions have declined a lot from ships as well. But for the NOx, they're still working on it. There is still an agreement in progress. In the really busy shipping lanes, such as through the English Channel between England and France, we can definitely see the footprint of that on the land in southern England. And in Portugal, having started working on the frame model for Portugal, that big shipping lane that goes north and south, even though it's fairly far out, we can still see it in the initial model results.
Yeah.
Oh, really?
Yeah.
For actually considering in the future to include the cruise lines, we receive a couple of big ships every day. They stop and start and
Yeah.
harvest and contribution
And
local.
they
Yeah.
have big blooms.
Yeah.
You can see them.
Yeah, their
And
local contribution.
it's not just clean CO2
huge.
coming out.
No.
So regarding the modeling process, more concretely the calibration phase, how did you calibrate the model? You are ready to say that you adjust the emission factors, but I want to know more concretely what you would use for the calibration phase.
So we are not actually doing that model calibration ourselves, it's colleagues of ours that do that. If I understand correctly, what they do is they take the monitoring network data and
From each station.
from each of the stations, and they compare that with what the model predicts, and then they pull the model surface
Yes,
to fit the measurement points.
but how do you put the emissions? You calibrate parameters or?
So the emissions, we can tweak the emissions if we know how to make them better and make them more realistic. And for that local landscape, we started off using UK average emission factors. So a UK chicken has an average emission factor of this many kilograms per hectare. But if you know what system the chicken is kept in, what type of house, you can apply a housing specific emission factor. So that's the first step of improving it, and you can only really do that for a local model because you don't know what's happening on every farm in the country. So that's something you can tweak locally. But then you still have to look at your model and calibrate it.
Can I ask a question for is that so that requires particular studies per farm type? Is that work done for most of the different types of farms, practices, land use types?
Yes, there's a lot of research going on because obviously mitigation practices cost money, so therefore you don't want to introduce something that doesn't actually make a difference. So all these injectors and training shoes and training hoses for manure, they do make a difference, but the farmers mainly use them because it helps them be more nitrogen efficient and also not to damage their crops. Because if you can get the slurry in underneath your grass rather than sprinkling it on top, you can get the animals on the field much more quickly. So there's all these practical implications as well. And obviously these studies of testing a mitigation measure for ammonia especially, that costs money as well. So it relies on the government saying, okay, we want to test this under local conditions. There are studies very often in Denmark or in the Netherlands or in other countries that have a strong mitigation policy, and they need to be able to prove to their farmers that it makes a difference. But if you then try and take Dutch emission factors or mitigation reductions into another country that has different temperatures or different plants or whatever, then or slightly different buildings, you can't just replicate that. So ideally you want to have country-specific measurements, and they cost money, and therefore they only get done every so often, and it's a small sample.
That's for both of you. Yesterday we were also discussing within the Natural Portugal project, with that this framework from UK to Portugal. One of the many things that we have to do as we go from UK to Portugal, one of them is the emission factors. They're likely to be different. We have many local emission factors that adapted to our animals, but the better we get, so the better we get to reality. And the way things are done in the field is also completely different from the UK to Portugal, the agricultural practices. So that also influences the models and the outcomes and how close they get to reality. So this is part of the work of actually tuning the model from place to place to make it better in each place.
And things like how to grow wheat. If you grow wheat in the UK, you either sow it in November and it does do hardly anything until the spring, or you sow it in March or April. Whereas I gather in Portugal, the wheat starts to mature in
Exactly.
March.
Because we're on the planet.
So it's a completely different system, and the nitrogen input and the opportunities for nitrogen losses are completely different. And you can't just say wheat emissions in Portugal are the same as wheat emissions in the UK or anywhere else. You need to look at the system.
And how do you manage when you have emissions coming from other countries?
This is where international collaboration and cooperation and these bodies like the UNECE Long Range Transboundary Convention are very useful, because you need to work together to reduce emissions. If you just reduce as one country, say the little Netherlands, which are in between France and Germany and Belgium, if they get a very large proportion of their position comes from other countries. The UK is quite lucky in that sense, in that it's sort of off to one side, there's a bit of sea in between, and Portugal is quite lucky in that it's to the west of all the countries, and the prevailing wind comes from the Atlantic. So
This is regulated by this international convention, the long range boundary pollution convention.
and the various protocols which then have these emission ceilings. So you remember Mark talking about the ammonia emission ceilings not being very ambitious. So for NOx and for sulfur, clearly everybody saw, okay, we need to do something because our forests are dying, our people are dying, blah, blah, blah. Ammonia, they're still not wanting to do things because the farming lobby is so strong. Some countries in Europe, such as again the Netherlands and Denmark, have got very strong nitrogen policy framework, and it's not just atmospheric, but it's also about nitrate leaching and everything else. And the farmers just basically have rules to follow, and if they don't follow them, there'll be consequences. In the UK, there is no such thing. For ammonia, there's a good practice guidance note. And actually, for the very large industrial pig and poultry farms, there are regulations. So they need to apply best available technology if they're near sensitive areas. But other than that, given that more than 60% of UK agriculture emission comes from cattle, there is no regulation of cattle at all.
But I suppose that the case of the Netherlands is kind of recent, because historically, I mean, they've been using manure, like, they changed their plant ecology a lot just because the input of nitrogen, because the fertilizer they used themselves was amazingly high.
Yeah,
So now they saw the disaster and now
it's very densely farmed, really, and very, not just densely, but also high intensity. And their nature reserves, they've actually started to take topsoil off to try and get rid of the accumulated nitrogen.
yeah.
And they have these relatively small nature reserves in a very busy area, whereas in the Scottish Highlands, there's nothing happening, so you just don't need to worry about local sources, because there aren't any. And the only thing with how you could reduce concentration of deposition in the highlands further is by doing something at a much larger scale and having international agreements.
Netherlands are spending a lot of money, for example, for restoring sand dunes,
Yeah.
which are completely changed in terms of native vegetation. And so that's why we should prevent.
Yeah. Preventing is
They know
better
the
than
price
curing.
now is very expensive.
Yeah. Any more questions? Thanks for listening.